start with our topic of why do we have seasons. First, we have to understand why we don't have seasons, right? So, 2 times during the year, the Earth, well, we know that the Earth moves around the sun, right, in a elliptical orbit. And because it is elliptical, right, during different times of the year we are closer or farther away from the sun. The ephelion and the perihelion are 2 names that they designate for being closer or farther away from the sun, right? So you can see with the ephelion, that's when we're farther away, and perihelion is when we're closer. This is why most people, when you ask them why we have seasons, they say it's the distance, right? But actually, if you look at the dates, right? So during January 3rd, we're actually closer to the sun, right? So that means that whole reasoning doesn't make sense, right? So if we were closer to the sun, you'd think that we would be hotter and it would be summer, right? But we know January 3rd that it's actually colder, and that's when we have winter, right? So this is not why we have seasons, right? So ephelion, perihelion are 2 designations to indicate when we're closer to the sun or farther away. To understand why we have seasons, we have to look at our tilt, right? So the Earth's tilt. Okay, so we are tilted. If you look at a globe, right, you can see the tilt, but this is showing you here our tilt, right, 23.5 degrees. Okay, as we move around the sun, right, it sweeps around and we get what's called the plane of the ecliptic. Right, so it's a designation for referencing basically to the sun. Right, so we are tilted 23.5 degrees from the perpendicular, right, to the plane of the ecliptic, right? So perpendicular meaning like a right angle, right? So this tilt, right, if we did not have a tilt on Earth, then we would not have seasons. So we will look at why we have seasons. It has to do with, we said, with that tilt, right? And if you look here, right, so our axis is right there. Right? Imagine an imaginary axis coming out of here. Right? So the circle of illumination, right, this right here, shows us, okay, we're starting with June 21st, right, and it divides the Earth into the daytime and nighttime hours. Right? It's best to look at kind of the upper regions, right? So think of the Arctic Circle, right? And as that moves around for a full 24 hours, then what's going to happen, right, is that it never goes into the darkness, right? So we have 24 hours of daylight up at the Arctic Circle. Okay, so farther north that you go, the more extreme this is. Now, where we're at, right, so kind of mid-latitudes, you can see the United States here, right? We don't go 24 hours of daylight, but we know that on our June solstice, that the daylight hours are longer and nighttime shorter, right? So if you put, put the Earth in the sun for a longer period of time, it's going to heat up more. Then we move to September 22nd, which is known as the equinox, right, meaning equal. You look at the circle of illumination, right, it's cutting the Earth in half, right? So 12 hours of daylight, 12 hours of nighttime. And then move again to December 21st, which is our winter solstice. Right? And again, if you look at the extreme, right, so look at the Arctic Circle, right, then 24 hours of darkness. Right? So less time in the sun, right, gets colder. This is what we know as our winter solstice. Right? And then moving again, right, to the equinox on March 20th, and we are back to equal again. Right? So 12 hours and 12 hours. In the different hemispheres, right, we will see that in the northern hemisphere, right, when we have our June 21st, right, the southern hemispheres we're experiencing summer, they're experiencing winter, right? So the seasons in the two hemispheres are opposite. Okay, another diagram here. It's the same diagram, right, except a different point of view, and we can see kind of more readily the entire Earth, right? So say June 21st, right, June solstice, our summer, okay? And then you can see, if you go to the southern hemisphere, right, South Pole, they get that 24 hours of darkness, right, while we're getting 24 hours of light up at the Arctic Circle. Okay, in addition to the length of day that changes, you also have different types of rays that emanate from the sun, right, and in regards to the placement of the Earth, right. So the Earth always maintains what we call parallelism, meaning that its axis always points to the same spot, right. So it's always pointing to the North Star in the sky, right. So the axis doesn't vary. As we move around the sun, right, the axis will either be pointing towards the sun or in December, as you can see, kind of like away from the sun. So this changes the placement of sun rays, right? So this shows you for the June solstice, right? So during the June solstice, we receive in the northern hemisphere more what we call vertical rays, right? So head-on rays. So it's the strongest intensity of light, right? And this is at the what we call the Tropic of Cancer, right? 23.5 degrees north. Right? And then as we look at the equinox, right, you're getting the vertical rays at the equator, right? We also call this the subsolar point, right? So the point on the Earth where the sun is directly overhead. Right, so subsolar point. Right, and then during December solstice, right, the vertical rays are at the Tropic of Capricorn, right, 23.5 degrees south. Right, so then these other rays, right, we'll see are more what we call oblique, right? So away from 90. We'll explain that in the next slide where you have kind of flashlights and stuff. It's a little easier to see. Okay, so if you have a plane surface, and I like to use the flashlight model, right? So this is a flashlight, okay? And then these are the rays coming out of the flashlight, right? So this is a vertical ray, right? And vertical meaning more at 90 degrees, right? If the sun comes in, right, so we have the flashlight, right, which is simulating the sun, right? So if we turn the flashlight a little bit, right, and cause the rays to kind of come down here like this, right? And the angle changes, right? So the angle that the rays are making with the surface, right? So this is like 45 degrees, right? But you'll also see that the distance in here, right, becomes greater, right? So the surface that it's covering, right? So we'll say this is, say, 1 unit. In this second one with 45 degrees, it's, say, 1.4 units. Right, so both the same flashlight, but it's covering a wider area, right? So that at any one point, right? And the oblique rays, the intensity of light is less. Right? And then if we go more extreme, right? So if it's really coming in at a very oblique angle, let's say like at, say, 35 degrees, right? Right, see all the distance it's covering, right? So we'll say that's like 2 units, right? So really less intense rays. Okay, so during our summer solstice, right, we are receiving more vertical rays than in wintertime. Okay, so to sum up, right, we have kind of 2 main reasons why we have seasons, right? And it all does begin with how we have our tilt, right? So that 23.5 degree tilt from the perpendicular to the plane of the ecliptic, right? And what this causes is the duration of day to vary, right? So that in our summer, right, we receive more, basically we have more daylight hours. And just like say a turkey in an oven, right, if you put it in the oven for a longer period of time, right, it's going to heat up for a longer, it's going to heat up more. Right? And then also the intensity of light, right? So during our summer, right, our June solstice, right, we are receiving more vertical rays. Right, so more of these, the 90-degree rays, right, which these more intense rays, right, we don't have, like at our latitude, we don't have completely vertical rays, right, it's not completely 90, but the angle, right, is more vertical, let's say, than, say, in the equinox or during our vernal time.